This is the fifth section of hyperbolic functions, and this is integrating hyperbolic functions. Now, there's advantages and disadvantages to doing this chapter. The advantage is that all of the integrals are given in the formula book. There aren't any you need to memorize. So you can use the integration section in the formula book, and you can also use the differentiation part backwards to help you I think it's integrate sec or sec squared, something like that, but they're all there, you don't need to memorize them. The disadvantage with this chapter is that really you need to have mastered all the different integration techniques from Pure 2. So before you attempt this chapter, make sure from the Pure 2 book you have done section 11.2, and I've got videos on all of these, integrating things of this type, f of ax plus b, so integrating things like that, which is actually using, well, I call it the reverse chain rule. 11.4, they call it the reverse chain rule. I call it actually looking for patterns, reverse chain rule. 11.5, integration by substitution. You'll need that for the last few examples. And 11.6, there are a couple of questions in exercise where you need to be able to do integration by parts. Now, I'm not going to go through all of those methods here, but as we go through the questions, I'll just mention briefly which method we are going to use to do the integration. Okay, this first example is of the type where we're integrating a function, and this bit here in the brackets is linear like this. So when we use this, we get something like this. Two steps. We integrate the outside. Okay, it's basically the stuff that's outside the bracket, and then we divide by the inside, whatever's inside the bracket, differentiated. Now, the reason I call it the chain rule, because this is the reverse of the chain rule for differentiation. So first of all, if we integrate the outside, cosh becomes shine. So shine x. With this, the inside of the bracket never changes and the inside must be linear. Then I divide by the inside differentiated. So the inside differentiated is 4. I divide by that. So then I stick a quarter in the front plus c. So that one is done. That's a nice straightforward one. Okay, so this one here, when we see two things in a numerator, not always, but if the top isn't like the bottom differentiator, you've got two things here, the first step is going to be to separate it out. So this is equal to integrating 2 over the square root of x squared plus 1 plus 5x over the square root of x squared plus 1 dx. Now, whenever you have two integrals like that, you can just put an integration sign in front of both parts. So we could write this as 2 over the square root of x squared plus 1 dx plus this integral 5x over x squared plus 1 dx, like this. Now, we've written them out. These two things look similar, don't they? So this and this look similar, but the methods are completely different. The methods are completely different for both. Now, there is a standard result that's in the formula book that says if you're integrating 1 over the square root of 1 plus x squared dx, that becomes arcsine x plus c. So this result is going to help us with the first bit. Now what I'm going to do at each stage, I'm going to make these things look as much like the thing I'm trying to get as possible. Now for the second bit, this is going to be useful, that when we integrate something of this format, you'll see it'll make sense in a moment. If I see something like that, then this is going to become f of x to the power n plus 1 over n plus 1 plus c. So this is going to be the second one, and you're going to see in a moment that the second part I can make look like this. So the first part, right, let's bring the 2 over to the other side. You are allowed to do that. Any constants come over to the other side. And I'm just going to swap the 1 and the x squared around. So can you see that this pretty much is going to become 2 arcsine x. So what can we do with the second part? Well, the first thing that I'm going to do is I'm going to write that x squared plus 1 at the bottom as a power, and that's going to be power negative a half. Now that looks a bit like this, where n is a negative a half and f of x is x squared plus 1. But if I were to differentiate x squared plus 1 to get like this pattern here, this should be 2x, but it says 5x. Not a problem, we can fix that. So let's keep this the same. Okay, I'm just setting this all up so that right at the end I can just change it for the integrals. Now I can change that. Now if I change it so that this is 2x, so it fits the pattern perfectly, like that, then what do I need to put in front of the bracket so it still gives me 5x once it's multiplied out? Well, I need to put 5 over 2 here. So that is exactly equivalent to what I wrote up here, which is exactly equivalent to this. Yeah, so all I've done is just write it in a different way, but writing it in this way allows me to basically just substitute in the integral there and to substitute in the integral there without too much fuss. So what I will have is, so I'll have 2 lots of that bit that I've highlighted in orange, so 2 arcsine x. Okay, I'm not going to put plus c because I've still got another integral. Now for the second bit, I've got this 5 over 2. Now that second bit in orange, that can just be swapped to the f of x n plus 1 over n plus 1, which is basically the f of x is the x squared plus 1. Okay, now that needs to be made to the power n plus 1, which is a half, divided by a half. So the last thing we need to do, obviously plus c at the end, last thing we want to do is we're going to tidy it up. So we've got 2 arcsine x. Now if I'm dividing by a half, it's the same as multiplying by 2, which means that basically this and this cancel out, just leaving plus 5 x squared plus 1 to the half plus c. We can leave it like that, or we can write that bit in brackets to the power half. We can write it as square root. Okay. Right, now part A is this pattern here. So f dash of x and then f of x to the power n dx, and to integrate that we would do f of x to the n plus 1 over n plus 1 plus c. So I'm going to make part A look exactly like that as much as I can. So the first thing I'm going to do, it's not really any maths as such, is to move this to the front and write the cosh 2x and put it in brackets to the power 5. Okay, it just makes things easier to do when it sort of matches up. Now, is the f dash of x right? Now, if I differentiate cosh 2x, I will get 2 sine 2x. So let's do that. So it's exactly right. So this would be f dash of x and cosh 2x to the power 5. But I can't just change the question to suit me. So to make it still the same thing, I put a half here. Now it looks exactly like that. What I can do is replace this part here. That's exactly the f dash of x times f of x to the power n. I will have half times by, and then I'll just apply the rule. This will be cosh 2x now to the power 6 over 6 plus c, and then we can tidy that up and get 1 over 12 cosh to the power 6 2x. So we can put the power 6 there, or we can put it in brackets and put it at the end. So that will be part A. Part B, I'm not quite sure why we're doing part B, because this is in the table. But I suppose what we could do is say, right, tanh is equal to sine over cosh. So we could write it like that. And then we could use another pattern which basically says that if you are integrating something where you've got the derivative over the function like that, then that becomes log of the bottom basically. So log of f of x plus c. Yeah, so if you didn't just look it up in the table, this is what you would use. Now let's have a look at this. When I if cosh x is f of x, so this is on my f of x, is that differentiated sine x? Yes, I don't need to worry about any numbers, that's perfect. So that means my answer is going to be log of cosh x. Don't think I need the brackets because cosh x is always positive anyway, or so the modulus, so it's always positive, but it's always worth putting in anyway. But as I said, this is in the formula book, so you know, in an exam, unless it told you otherwise, if you see that, just go straight to the formula book and write down that. Now, in these questions here, oh look, there it is. Just said it was in the formula book, and there it is, it's there. We won't need it on this one though. Yeah, these ones we're going to use trig identities to help us, because as it stands, these can't be integrated. You might be tempted to say, right, let me use the reverse chain rule with something like this, but you can't. This bit in the brackets needs to be linear. If it's non-linear, you cannot use the reverse chain rule, and that is not linear. It needs to be of the form ax plus b. So reverse chain rule, bye-bye, don't work. So we're going to have to use a different method here, and we're going to use a trig identity to help us out. So what have we got here? Cosh squared 3x dx, and the cosh squared appears in the identity of cosh 2x, and that is 2 cosh squared x minus 1. Yeah, that's where that identity appears. Now if we rearrange that, we'll get cosh x is equivalent to cosh 2x plus 1, and then that's all divided by 2, but that might be more helpful to write it in the form half cosh 2x plus a half. So that's what we're going to do the replacement. But here, can you see we've got cosh 3x or cosh squared 3x. So all we need to do, if this is a 3 here, this is going to be double that. This will be a 6. So 3, that'll be a 6. So it'll be half cosh 6x. So that's the only difference, rather than just x, it's 3x. So everything gets times up by 3. So using that identity, we will instead be trying to differentiate half cosh 6x. So we've got rid of that squared, plus a half dx. So to make things even easier, we'll take the half over here as a factor out of both things. So then we have cosh 6x plus 1 dx, and then from here we'll have half, and now we can integrate the cosh 6x using the reverse chain rule. So that will be that we integrate cosh to become sine 6x, then we divide by the inside differentiated, so actually we divide by 6x, so we're going to have 1/6 here, oops, in black, and then the 1 will just become x plus c, and then I'll expand out the brackets, and that will give us 1/12 sine 6x plus half x plus c. Now part B, there's a little trick we can use with this sine cubed x, and that is anytime you get like an odd power like 3, 5, 7, 9 with cosh or sine, is that we're going to write it like this as sine x times by sine squared x dx. What that means is we can then use the identity cosh squared x minus sine squared x is 1. Yeah, so that means that we can rearrange that to give cosh squared x minus 1. So that will be the next step. Let's write that down actually. So that would give us sine squared x is going to be cosh squared x minus 1. So we'll put that in as a substitution. So sine x times by, and that's going to be now cosh squared x minus 1. Then expand the brackets. So it now becomes sine x cosh squared x minus sine x dx. Then for this bit here, we can use, for all of this bit here, we can use the pattern where we're integrating f dash of x, f of x to the power n, which will integrate to f of x to the n plus 1 over n plus 1. So here, the f of x is going to be cosh x, n will be 2, and then the f dash of x, that'll be shine x. So it sort of fits the pattern nicely. So that means the first bit, when we integrate it, that will be cosh cubed. So basically we're just applying this bit here. So it'll be cosh cubed over 3, which is 1/3 cosh cubed x. So 1/3 cosh cubed x. And then the shine will just differentiate to cosh. That's just a standard result. So minus cosh x plus c. So there's our final answer for part B, and our answer for part A was over here. Right, now whenever we get a hyperbolic function times by an e, then what we do, we're going to write the hyperbolic function in terms of e. Now we know that shine x is equal to e to the x minus e to the minus x over 2. So if we write shine x as that, then actually everything's in terms of e to the x then, and then we can easily integrate it. Now you'll need to know that when you integrate e to the x, you will get e to the x plus c. Now we can use the reverse chain rule on this. So if you have e to the ax plus b, so some sort of linear thing in a bracket, which we can think of as like the inside, then we use the reverse chain rule, which is to integrate the outside, so that just becomes that, and then divide by the inside differentiated. The inside differentiated as a, so you just divide by 1 over a. So it's going to become like that if you've got something other than e to the x. Right, so let's do the substitution. So you've got e to the 2x, and then shine x, we'll put this e to the x minus e to the minus x over 2 dx, and then we'll multiply out the brackets. Now remember, when you multiply, you add the powers. And now the other thing I'm going to do, I've got divide by 2, so let me take that across first. Always take constants across. Yeah, it just makes things easier. Yeah, there's less there to sort of frighten you. Right, so multiply the brackets, adding the powers. So I'll get e to the 3x minus e. Now if I've got minus x plus 2x, that becomes e to the x dx. So actually, the only thing that I need to integrate now is that thing that's in a bracket. So it's going to be half. So e to the 3x using the reverse chain rule, that's going to be 1/3 e to the 3x, and then the minus e to the x, well that just becomes e to the x, like that, and then that's plus c. So if we multiply out the brackets, I'll get 1/6 e to the 3x minus half e to the x. There should be an x there. Right, so here's our final answer here. So yeah, because we had an hyperbolic function times by something here, we've got e to the x, then use your hyperbolic function given in terms of e to the x there, and just multiply out, simplify it, and then integrate. This is a substitution question, and here's 3 substitutions that are going to help you. So a lot of this integration is all about looking for patterns, right? So let's say you want to integrate that. The substitution you will make is going to be x equal tanh theta or tanh u. I'm going to use theta, they use u in the book. If I want to integrate 1 over the square root of a squared plus x squared, the substitution that I make is going to be x equals a sine theta or sine u. And if I want to integrate 1 over the square root of x squared minus a squared, which looks like the question that we're doing here, then the substitution we make is going to be x equals a cosh u or a cosh theta. So let's do that. So the first thing we're going to say is let x equal a cosh theta. If I substitute that in, I'll have 1 over the square root of a cosh theta all squared minus a squared dx. Okay, now we also, remember, need to substitute the dx for du. So if x, or d theta in this case, if I've got x equals a cosh theta, then dx d theta or du, if you use cosh u, is going to be a sine theta or a sine u. If I rearrange that, I'll have dx equals a sine theta d theta or du. So this I'm going to use to substitute the dx with that. So what I'll have now is 1 over the square root. Now if I square the a cosh theta, I end up with a squared cosh squared theta minus a squared, and the dx I can change to a sine theta d theta. Now the bit at the bottom, I can use this identity, cosh squared minus sine squared theta is 1. So I could rearrange that, and if I multiply everything by a squared as well, so let's multiply by a squared first. I'll get a squared cosh squared theta, and I'll take the no I won't, yeah, I'll bring the 1 across, so I'll get minus a squared equals, was equivalent to sine, or a squared sine squared theta. So all I've done is using this identity here. So using this identity, all I've done is I multiplied everything by a squared, and then moved the sine over to the right and the 1 over to the left, or what would be a squared, and I end up with this. Now you'll see that I can now take this, which is what I've got written underneath the square root here, I've got that written there, and I can change it to a squared sine or sine squared theta. So let's do that. That's the next step. So that will give me 1 over the square root of a squared sine squared theta. That's still a sine theta d theta. So I'm integrating everything with respect to theta here, or it could be u if you use the u substitution. Now what's going to happen is the square and the square root is going to cancel out, just leaving 1 over A sine theta, and then that will cancel out with the A sine theta there, so that cancels out. So all I'm left with is the simplest of integrations, integrating 1 with respect to theta or respect to u. So what am I left with? Actually, that just becomes u plus c. Okay, so now we need to substitute back. Oh, actually, sorry, that will become theta plus c, not u. I'm so used to using u. Theta plus c. Right, now, what have we got here? Look at this. Let's rearrange that so that we can substitute. So what did we have at the start here? X equals a cosh theta. Divide both sides by a. X over a is cosh theta. Do arc cosh of both sides. Theta equals arc cosh of x over a. So that's what we're going to replace our theta with. So this mammoth question here, we've now got a final answer of arc cosh x over a plus c. So there's our final answer. So these little substitutions at the top, these are useful. Yeah, these are very, very useful. Okay, this one's much more straightforward because we can simply compare this to this that's given in the formula book and straight away write down what the integral is, what the result of the integration is, r cosh x over a. So all we need to do is work out what a is. And in this case, a is going to be 4 because we have x squared minus 16. Here it needs to be in the form x squared minus a squared. So a is 4. So what we could do is when we write this out, we could write this as 1 over the square root of x squared minus 4 squared. You could write it like that. That might be helpful. Now what does that equal? That's going to be r cosh x over a, so x over 4. And in a moment we'll substitute in the values of 8 and 5. So let's work out what that is. So first of all, we've got r cosh 8 over 4 minus r cosh 5 over 4. So that becomes r cosh 2 minus r cosh 5 over 4. Now how do we work this out? Well, in the formula booklet, I think it's on page 14, it says this, that r cosh x is equal to log x plus the square root of x minus 1. Yeah, so that's given to us in the formula book. All we need to do now is substitute the values in. So let's do that next. So r cosh 2 becomes log 2 plus square root 2 squared minus 1. Okay, minus log, and then r cosh 5 over 4 becomes log 5 over 4 plus square root 5 over 4 squared minus 1. Right, so what does that become? Well, the first bracket becomes 2 plus 2 squared minus 1 is 3, so log 2 plus root 3. The second bracket becomes, well, I'll have 5 over 4 plus, now 5 over 4 squared is 25 over 16. 25 over 16 minus 1 is like taking away 16 over 16, so we're left with 9 over 16 over 16. Right, and the square root of 9 over 16, it's like they choose these numbers deliberately to make it easy in the second bracket. So that'll be 5 over 4 plus 3 over 4, which is 8 over 4, which is 2 log 2. And then last thing, when you're subtracting with logs, the rule says you can do it as a division. And that looks exactly like what we started with. It has been proven. Okay, here's another substitution question. But what you may have noticed is that anytime we have this something like this or something like this, when it's not even 1 over, that the substitution, what we make x, always seems to be like shine u, and this fits the pattern. And you'll also notice that when this is a minus, it seems to be cosh u. So our substitution here is going to be x equals shine u. Now we need to find that's going to be dx du, because we need to replace the dx. That'll be cosh u. So from there we can get dx equals cosh u du. Okay, and we'll do this bit for the end actually. From here, if we do arc shine to both sides, we end up with arc shine x equals u, and that's going to be useful right at the end. Right, so let's start. Let's do our substituting. So we'll end up with 1 plus x squared, or 1 plus shine u squared. We want the square root of that. And we're going to replace our dx with cosh u du. So after that, the 1 plus shine squared, so this bit here, that can be replaced with cosh squared u. So you'll remember the identity cosh squared, if I write it with u, plus sine squared, sorry, minus sine squared u is 1. So if you rearrange that, then you can see that you can put cosh squared u there. So that will give us integrating the square root of cosh squared u, and you can see that's going to cancel out the square and the square root, cosh u du. And what that will leave us with is basically cosh squared u du. We want to integrate that. Now I can't use the reverse chain rule. I need a substitution, so we use like the cosh double angle. So cosh 2u is 2 cosh squared u minus 1. So if I rearrange that, I'll get cosh squared u is equal to, now it's going to be, if I move the 1 over and half it, it's going to be half of cosh 2u minus 1. So I'm going to make that substitution. So that will give me, and I'm going to move the half to this side of the integration sign. So I've got cosh 2u minus 1 du. So now let's integrate. That's going to be half. Now the cosh 2u, using the reverse chain rule, or what I call the reverse chain rule, will become half sine 2u, and the 1 will become u, like that. And the last step is just to substitute back, but notice right at the start here I prepared the way, so now that can go into this. So to enable me to make that substitution in the first part, this sine 2u is a double angle, and sine 2u is equal to, or equivalent to, 2 sine u cosh u. So we're going to use that to change the sine 2u, and that will give us, and we've got halves all over the place. Right, let's do this. Half times by half, I know I'm going to have 2 sine u cosh u minus a half u plus c, and I suppose I should have had the plus c there. Now we can do the full substitution, so I can see that these cancel out there. Right, doing this bit by bit. Sine u becomes x, so we need to take everything back to x's. So I've now got half x. Now the cosh u, I need to change that back. I'm gonna have to use an identity to get that back. So let's do that over here. We've got identities left, right and center. Right, so we're going to be using this one again. Cosh squared u minus sine squared u is 1. Right, okay. Moving the sine squared across and square rooting both sides, I will get cosh u, not squared, just cosh u. Cosh u is going to be equal to, or equivalent to, the square root of 1 minus sine squared u, which is like 1 minus x squared. So the cosh u I can change to the square root of 1 minus x squared. Then minus half u, so that's half, and my u is up here. There we go. So I'll replace the u with arc sine x. Arc sine x, and we mustn't forget the plus c. So there we go. That's that one. Okay, the first thing to note on this is what I have in the denominator. What I have in the denominator is like this: x squared plus a squared. Now whenever you see anything of that type in the denominator underneath the square root, then the substitution you make is x equals a sine u. So that's going to be the first thing that I write down. X equals, now in this case, a is 3. So the substitution I'm going to make is a equals 3 sine u. Now you could use theta instead of u, or any letter that allows you to do a substitution. Right, so I also need dx du. So that means differentiating that, and that will give me 3 cosh u, and then I'll rearrange that so that I get dx. So I can substitute that as 3 cosh u du, cosh u do, and I also need to change the limits. So the limits I have are x limits, and I need to change them to u limits. So I use the substitution to do that. So I'm going to use this to do that. So if x is 6, I will have 6 equals 3, not cosh, 3 shine u. So I'm basically going to work out what u is. So I'm going to divide both sides by 3. So I get 2 equals shine u. And then the next step is to do arc shine of both sides. So I'll have u equals arc shine 2. Arc shine 2. N is a bit big. Right. Now I do the same thing with the other limit, which is 0. So I'll write 0 equals 3 shine u. So again, the same thing I want to do is to work out what this is in terms of u. So divide both sides by 3. That will just leave me with shine u equals 0. Then we do arc shine to both sides. So u equals arc shine 0. And that will give you, you can actually work that out on your calculator. If you press option straight away and you get the hyperbolic function menu, and you'll see shine inverse number 4, you put in 0 and you end up with 0. So u equals 0. So now we're ready to substitute all of this in. So first of all, the limits, 0 at the bottom, arc shine 2 at the top. Now unfortunately we can't write it any more exact than that, because if you type that in your calculator you don't get an exact answer. Remember, it's going to be the natural log of something, and we'll probably need that later on. Right, now at the top we're going to have x cubed. Now if x is 3 shine u, then x cubed is going to be 27 shine cubed u. So that's going to go at the top. 27 shine u cubed over the square root of x squared. So x squared is going to be 9 shine squared u plus 9, like that. Okay, and the dx is going to get placed with 3 times by 3 cosh u du. Now the shine u at the bottom, or shine squared u, we're going to be using the identity cosh squared u minus shine squared u is equivalent to 1. So that means that we can replace shine u with cosh u minus 1, with cosh u minus 1. So let's put that in. That's going to be our next step. So if I put equals, so I've still got arc shine 2 here, 0 here, then 27 shine cubed u over, now this will be the square root of 9 lots of cosh squared u minus 1 plus 9, then times by the 3 cosh u du. Now if we sort of tidy up the bottom, then what will end up, basically all of this here, you'll have 9 cosh u squared minus 9 plus 9, so the 9's will cancel out. You'll just be left with 9 cosh squared u, and then if you're going to square root that, you'll just end up with 3 cosh u. It'll just end up, so I'll just write it down. All of this just ends up to be 3 cosh u. Now look, we've got a 3 cosh u here. So those are going to cancel out. So all I'm going to be left with is, just write it down here, 27 sine u du. Okay, so we've got a lot cancelling out there. I haven't written those steps down, but I've sort of talked through them and talked through what will happen. Right, so let's move the 27 over to the other side. So move the 27 over there out of the way. So it's a bit easier. So now it just becomes integrating actually cos cubed u. There you go. So we just need to integrate that. Now we came across one like this before, and we said that if we write this, like odd powers like this, if you write this as sine u times by sine squared u, then use the identity, this identity here, and replace the sine u from the sine squared u, then what this will become, so I'm just going to do this in little steps down here, is cosh squared u cosh squared u minus 1. Okay, so that's this bit here substituted times by sine u, which if you expand the brackets becomes cosh squared u sine u minus sine u. So actually I'm going to write that down here. So I'm just doing all of that so it's in a form that I can integrate. So that sine cubed u eventually becomes cosh squared u sine u minus sine u du. Now the second bit's no problem. We can integrate that. That'll become cosh u. And then for the first part, it follows this pattern. So this bit here is like that, f dash of x, f of x to the power n. Yeah, it's that pattern, isn't it? And so it becomes f of n to the power n plus 1 over n plus 1. So that's what we're going to use to integrate the first part. Right, so that becomes this 1/3 cosh cubed u minus, make a bit of space here, minus cosh u, so let's put that down, minus cosh u, and that's between the limits 0 and arc sine 2, arc sine 2, which we mustn't forget to multiply by the 27. We've got the 27 there and the 27 there. And once we evaluate that, and you'll get 18 root 5 plus 18. Now you can evaluate actually the answer on your calculator, but it won't give you the answer as a surd. It will give you a decimal answer. Okay, so you'll notice all the ones we've done so far have been like this sort of format. Maybe it's had an x or x squared at the top and we've done something slightly different, but they've been like this. Yeah, and we've made the substitution of either a sine u or a cosh u, depending on whether it's a plus sign that's there or a minus sign that's there. So when it was a plus sign, we made that substitution. If it was a minus sign, we made that. Now you'll notice that this question we've got here isn't of that format because we've got this 12x and we haven't got like a nice square number there. Now we're going to make it look like the other format, x squared plus or minus a squared, by completing the square. If we complete the square on the bottom, we can make it look like this form of x squared plus or minus a squared, then we can proceed from there. So what we're going to do is we're going to complete the square on 12x plus 2x squared. So the first step, if we're completing the square, you need to take the 2 out. So that would leave x squared plus 6x. And then actually we're only going to be completing the square on what's in the but what's in the bracket here. So we'll complete the square on that. So that'd be 2. Then we're going to have x plus 3 all squared. So that'll give me the x squared and the 6x, but it will also give me a plus 9, which I need to remove. So I need to do minus 9 there. So now we've completed the square on the denominator. So what we write now is this. I'm going to integrate 1 over, and it's going to be the square root of all of this to, I need 2 brackets, x plus 3 squared minus 9. Now the 1 over square root 2 can be taken to the other side because you can split up that denominator. It's basically like square root of 2 times the square root of x plus 3 minus 9. So let's move that to the other side. So 1 over root 2. The more constants you can take over to the other side, the better. It just makes it look a bit easier. And then we've got 1 over the square root of x plus 3 squared minus 9. Now that looks more like what we're used to. Yeah, and we can do something with that. And this substitution is actually quite straightforward. We're going to now let u equal x plus 3. Yeah, just that bit in the bracket. And so if u is equal to x plus 3, du dx is going to be 1, which means du equals dx. So let's do that substitution. 1 over root 2. And then integrating 1 over the square root of, it's now going to be u squared minus 9. See how it really looks like, you know, the thing that's in red at the top, du. Now from here, we don't need to like substitute in cosh u and do all of that. This is one of the results that's in the formula book. So it tells us, and the result is this, that if I'm integrating 1 over the square root of x squared minus a squared dx, that becomes r cosh x over a plus c. So in our case, it's the same. I've just got u instead of x, and a would be 3 in my case. So I can just write straight down now that I'm going to have r cosh, and it's not going to be x, it's going to be u over 3 plus c. And that's it. So that's our final answer. Yeah, so a slightly different technique on this one. Okay, this question is going to be a little bit easier because we have a substitution. So first thing we'll do is we'll write out what that substitution is. If we expand the brackets like that, then we'll work out dx du. So it's not du dx, dx du, which will just be 2 shine u. Then we'll multiply both sides by du and we get dx equals 2 shine u du. Okay, so what's of interest? That's going to go where the x's are, and this is going to go where the dx is. So let's make the substitution first into this 4x squared minus 12x minus 7. So that'll be 4, and this is our x, 3 over 2 plus 2 cosh u there, and that's squared, minus 12 times by, that's going to be 3 over 2, not 3 over 3, what am I that for? 3 over 2 plus 2 cosh u, and then minus 7. Right, some expanding to be done. 3 over 2 times 3 over 2 is 9 over 4. Then 3 over 2 times cosh 2u is going to be 3 cosh u. Then we're going to do that again. So we'll have 6 cosh u. Then 2 cosh u times 2 cosh u is going to be 4 cosh squared u. Okay, then multiplying at second brackets, we'll have negative 18. And then minus 24 cosh u minus 7. First bracket multiply out the 4, so we have 9 plus 24 cosh u plus 16 cosh squared u minus 18 minus 24 cosh u minus 7. Let's put that all together. Now see that we have a 24 and a negative 24, so they cancel out. So I've got 16 cosh squared u, and then I've got 9 minus 18, and then minus 7. That'll give me negative 16. Okay, and actually what I notice here, I don't really want to be substituting that in underneath the square root, but by using this identity, the cosh squared u minus shine squared u is equivalent to 1. If I were to times both sides by 16 and move the shine u across, basically this is the same as 16 shine squared u. That's much nicer to put underneath the square root because that's going to be easy to square root, isn't it? Rather than trying to square root 16 cosh u minus 16. Yeah, which I suppose we could do using the difference of 2 squares, but then well, no, don't even want to go there. Right, always looking for the easy root. So it's going to be 1 over the square root of 16 shine squared u. Now we mustn't forget about our du, so we're going to have times by 2 shine u du, like this. So the bottom of this, when you square root it, is just going to become 4 shine u. And then you're basically going to, well, the shine u's are going to cancel out, aren't they? Or at least 2 of them at the top. And just leaving you with 2 at the bottom. So in effect, all we're going to be doing is integrating a half. And when you integrate a half, what you're going to have half u plus c. Now we need to substitute back. And to do that, we're going to take our initial substitution, which was this. And what we're going to do is we're going to rearrange it to make u the subject. So I've got x minus 3 over 2 equals 2 cosh u. Then I can divide both sides by 2, so I'll have half x minus 3 over 4 equals cosh u. And then if I do arc cosh to both sides, what I'll have is u equals arc cosh of a half x minus 3/4. So that substitution can go in, giving us a final answer of a half u, which is r cosh a half x minus a 3/4 plus c. Okay, you should now be able to do exercise 6c on pages 140 to 142 of the textbook. Now I've pasted in here all the information that you're going to find in the formula book. Okay, so you've got all the integrations listed there. You've got the identities listed there as well under the hyperbolic functions, and the definitions of the inverse functions arc cos, arc sine and arc tanh. So they're all over this side over here. So we've got our integrations here. Now the reason I've put the differentiation one is because if you are asked to integrate, let's say for example, sec squared, which is this one, you'll notice it's not in the table. But we can use this backwards. So what you can do, you can integrate sec squared by using this table in reverse. I think all the others are actually in the integration, but that one isn't. Okay, and if you see any others, again, you can use this table in reverse and use it like an integration table. That's number one. So you can use that one backwards. So if it's not in the integration part, go back to the differentiation part and see if it's in the right hand column and use it backwards. So let's have a look and remind ourselves of the different methods. So first of all, is it possible to split a fraction up? Can you split it up? You split up a fraction, almost like partial fractions. If that's possible, then do it. Can we do it by looking for a pattern? So if I see this, or I can make it like that by playing around with the constants, then actually I can just apply this rule. So add 1 to that power, divide by the new power, and then it's plus c. There's another pattern. So if I see something like this, again, if I can play around with the constants to make it look exactly like that, it does make things easier. Then that's always the natural log of this bottom part, plus c. Is it possible to use a trig identity to change things around? Okay, think about those, the odd powers of trig. So things like sine cubed x, for example, or cos cubed x. Yeah, we have ways of doing that. So look back at the that example to see how to do it, and then you might use like one of these trig identities up here. Once you've written maybe sine cubed, you'd write it as sine squared times sine, or cos cubed, you'd write as cos squared times cos, and then you can make a use a trig identity. Then there's substitution. Now with substitution, if you see, and I'll just recap this again. So if we had something where you've got this pattern, 1 over a squared minus x squared, I don't think there are any like that in the book, then your substitution will be x equals tanh u There may be one in the exercise like that. Or if you see something of this pattern, it may not necessarily be 1 at the top. It may be like x or x squared. Then but if we see something like x squared plus a squared plus x squared, then our substitution is going to be x equals a shine u. And then if we see something like this, same type of thing but with a minus sign, so x squared minus a squared, then our substitution is going to be x equals a cosh u. And the last type is if you see one of this form, so 1 over basically a quadratic. So let's say it's this form, px squared plus qx plus r dx. Then the method for this one is to complete the square, but you need to take out p first. Take out that coefficient of x squared first, then complete the square. So complete the square. So I think that now completes all of the methods, and there may be methods that you learn from Pure 2 as well. So just be aware that you may get integration by parts. Integration by parts. So it could be any one of those multiple methods that we use where we solve these integrations that involve these hyperbolic functions.